Okay, guys, we're coming into the last part of the Unit 6 material that we're going to look at. And I kind of liken this to Chapter 3, which is when we just did the derivative rules. So this integrating indefinite integrals using substitution, this is our technique for integrating where there was a chain rule involved. And so we've already done the notes on basic integration and finding antiderivatives for your easy derivative functions that we learned back in Chapter 3. So if you have a known derivative, or you can manipulate the integrand into a known derivative, then we can very quickly integrate and find an antiderivative. And we do a lot of that with power functions and trig functions. And some of the recognized antiderivatives, like the antiderivative of 1 over x, is the natural log of the absolute value of x. The antiderivative of e to the x is e to the x. The antiderivative for a power function, remember to add 1 and then divide by that new power, and so on. So there are several of these basic ones that we've learned, and we learned a little bit of manipulation with algebra to transform the integrand into a known derivative. So now we're going to look at some examples, and I'm going to work through this where I'm going to pause the video and let you guys do a little bit of work on your own as you're looking at this. This really works better in the class in a group setting, but we're going to kind of go with it here. Now, the question we have here is which one does not belong? So we've seen some integrals that are easy to solve because they simply reverse the differentiation process. But there are many others that do not follow our basic rules. We had a lot of more complicated derivative rules like chain rule, product rule, quotient rule, and so on. And so when we work backwards, there are going to be different techniques for these more complicated rules. In AB calculus, the only more complicated technique that we're going to be working backwards from is chain rule. When you take the second semester of calculus next year, you will look at other techniques of integration that will work backwards from product rule and quotient rule and some of those other things. All right, but there are also a lot of integrals that can't be solved without technology. And we did see a little bit in an example previously where you do have a function int command on your calculator. So your calculator will take integrals, definite integrals, for you. Well, actually, we haven't seen that yet. Sorry, I'm confused on what notes I'm on. We will see that there is a calculator command called function int. Just like you can find the derivative at a point, we can find the integral using the calculator as well. But let's look at some that you should be able to work backwards from. So what I want you to do, I'm going to put a little timer on for 2 minutes. And what I would like you to do is take a look at both number 1 and number 2 here in the set of notes. And in the set of integrals shown below, there's one that can't be solved by hand without using the calculator. And there's one that you should be able to, quote unquote, recognize what it is the derivative of. So kind of think about how derivatives work, how chain rule works, and complete number 1 and number 2 for me. And I'm going to put a timer on for 2 minutes. I feel like I should have put the Jeopardy music on if you're still listening to this, or if you just paused it because you're just going to go ahead and fast forward to the end of the 2 minutes. But you know, the do 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 do. Sorry, a little punchy. It's only 7:52 in the morning. Alexa, play Jeopardy music. You have Jeopardy. Enable. Want to open it? No. See, that didn't even work. All right, so coming back in and taking a look at what you should have done for this part is that when you look at it, the first one, very straightforward. You have your antiderivative of cosine. Cosine is a known derivative, and we know that cosine is a derivative of sine. Now, did you guys remember your plus c? Notice that I have plus c on all of these ones that we've done because you're doing a general antiderivative, so you need that constant. Now, looking at the two that are below here and kind of talking about the difference between them, that when you see this, while cosine itself is a known derivative, that cosine is a composition. And we know that when we have a composition, that the derivative of a composition requires chain rule. So let's just kind of make a note to ourselves up here. Let's see, what color do I want? Let's do this in blue. That when you are doing the derivative with respect to x of something that is f of g of x, right? So you remember our chain rule problem. That you take the derivative of the outside function, leaving the inside function there, and then you times the derivative of the inside function. So when we are looking at the quote-unquote known derivatives, the form of the known derivatives are going to have to be where you have a known derivative here, which would be the outside function. And we need to make sure that included in the integrand is going to be the derivative of the inside or the derivative of the stuff, as we were talking about how we taught that. So we're looking for things in the integrand that are of the form of f prime of stuff times the derivative of the stuff. So this is kind of our key idea that is what we're looking for, the form of the integrand. So if we come back and we take a look at this, when I am highlighting this 2x right here, we're basically recognizing that that 2x is the derivative of x squared. So that's supposed to be there in the known derivative, because if we had done a chain rule derivative, we would have included the derivative of the stuff. And you can see this over here. If I was taking the derivative, now again, you can always check your answer on these. If I'm taking the derivative of the sine of x squared plus c, the derivative of sine becomes cosine of the stuff. And then you follow that with the derivative of the stuff, and then of course the derivative of the constant is 0. So we're basically just practicing working backwards. Now, a lot of these, this is what we call sight recognition or pattern recognition. We don't actually have to do a quote-unquote substitution technique if it is very straightforward and we can recognize that this is the known derivative of a chain rule problem. As long as you kind of, we like to call it, recognize that you have your derivative of your stuff outside, and then realize that it's only there because of chain rule, and we kind of pack it back up. You can almost ignore the 2x. Notice when they come over here to the general antiderivative, there's no 2x in it because that was the derivative of the stuff. I kind of packed it back away, put it back inside with the inside function, and I don't really use that at all. It just has to be there to be the quote-unquote known derivative. So that's why here our one that was not possible, I'm going to highlight it in kind of a pinky red here. The one that is not possible was the cosine of x squared, because the only way that we could do that antiderivative is if there was the derivative of the stuff somewhere as part of the known derivative, that we needed this in order to be able to accomplish that derivative. All right, so now in the second set down here, all right, let's look at which ones I want to highlight. Hopefully you remembered that the antiderivative of 1 over x is a known derivative. That was the generic rule, and that gave us the natural log of the absolute value of x. Now, kind of as I'm looking through these, the ones that are interesting, the first one was not too bad. And I'm going to start to show you a little bit about why we do this kind of U substitution. In my head, I'm thinking about the derivative of the stuff. So I'm thinking about what is the derivative, let's do this in blue. What is the derivative of this x minus 3 with respect to x? And in this case, it's 1. And so when I look for that, it's okay that there's a 1 in the numerator of that first problem because the derivative of x minus 3 is 1. I already have the derivative of the stuff there. So we can go straight to the answer that we are looking for here, which is this ln of x minus 3. So you see how this 1 over stuff, and then it's the ln of the stuff plus c. Now, I'm going to skip the one that's got the green next to it. Let's go down here to the bottom. When I looked at this problem down here, I am looking at the stuff that's in the denominator, and I'm recognizing that the derivative of x cubed minus 3 with respect to x is going to be 3x squared. So notice I kind of rewrote this so that when I was looking at it, that the format is 1 over the stuff, and then right here is the derivative of the stuff. So I was kind of making sure that I had all of the parts needed for the known derivative of a chain rule problem. And then I can pretty much pack the derivative of the stuff away and look at it in terms of just this natural log of the stuff and plus the c, of course, and we could do that. All right, now, this is also why kind of looking at the next to the last problem, the 1 over x squared minus 3. Now on that one, it is not possible. You can see that the stuff at the bottom is the x squared minus 3. So in looking at that, the idea is if this had been a chain rule problem, then we would have had the derivative with respect to x of x squared minus 3. We would have needed a 2x somewhere. And this is missing in this problem. And so looking at that, we don't have the derivative of the stuff, and so that's not going to be possible. All right, but now let's look at the one that I have in green here, because that one is something that you might have originally said, hey, I can't do that one. It's missing the stuff. Well, there's a caveat to this derivative of the stuff that we're looking for. Remember that constants can kind of move in and out of integrands because the constant is kind of like a rider and it doesn't really affect anything. And so when I looked at this problem, what you're seeing when you look at it is the fact that when I'm doing the derivative of the 2x minus 3 with respect to x, and I'm supposed to have a 2, I realized that, hey, I was missing the derivative of the stuff. But if what you are missing is a constant, we can actually correct for any missing constant. We're using a trick. And our trick is that remember that we can always multiply by a form of 1. And that form of 1 does not affect the actual problem. So notice that I added a 1/2 here on the outside, and I added a 2 on the inside. Technically, you can add both the 1/2 and the 2 on the inside, but then you immediately are going to move the extra 1/2, the corrector constant, pull it to the outside. And so what you've done is you basically multiplied the integrand by a form of 1. And so when I do that, now I have the quote-unquote derivative of the stuff that I needed in there. All right, so here was my stuff. And then that is now the derivative of the stuff included. So I have it in the proper notation for use of chain rule. And so sometimes you might need to add a corrector. Now I just want to make it very clear before this video ends, the only thing you can correct for is a constant missing. You cannot correct for a variable that's missing. So we cannot correct here. Okay, we're going to stop and we'll start with the